There's a hydrogen helicopter program happening right now that most people haven't noticed. Not because it's futuristic, but because it's already past that stage. It's in the phase where the real problems show up: integration, control, certification, the exact place where most hydrogen aviation projects stall. Robinson Helicopter Company, the same manufacturer behind the most widely operated light helicopter in the world, is currently refining a hydrogen fuel cell propulsion system for its R66 platform. And the reason this matters isn't the headline, it's the engineering phase they're in, and what that phase tells us about where hydrogen aviation is actually headed. This isn't a concept. It's not a render. It's a pre-certification engineering program, actively working through the exact problems that have stopped every other hydrogen aircraft from getting off the ground at scale. So today we're going to break down what's actually happening, how the system works, what Robinson is specifically refining right now, and, critically, where the real friction still lives. Let's start with some grounding context. Robinson's R66 is a 5-seat turbine helicopter. It's used across the board: emergency medical services, law enforcement, utility inspection, offshore transport. It's not a niche aircraft, it's a workhorse. That matters because when you choose a workhorse platform for a hydrogen conversion program, you're not building a demo. You're building toward a real operational replacement. The program is currently in what's called the engineering validation phase. That means the core concept has already been established. Yes, a fuel cell system can power this aircraft. And the work now is about refining that system to the point where it's safe, reliable, and certifiable under aviation standards. A first hydrogen-powered flight is being targeted for around 2027, with full certification further out, around 2030. That timeline might feel slow if you're used to software or consumer electronics. But in aviation, a 5-year runway from engineering validation to certification is actually moving. The FAA and EASA don't let you rush airworthiness, and they shouldn't. What Robinson is doing by entering this phase now is getting ahead of the certification queue, which is a strategic move, not a delay. Now let's get into the architecture, because this is where it gets interesting and where a lot of coverage misses the point. The R66 hydrogen platform uses what's called a hybrid electric propulsion architecture. The core of the system is a PEM fuel cell, proton exchange membrane, which generates electricity by combining hydrogen and oxygen in an electrochemical reaction. That electricity powers an electric motor which drives the rotor system. The only byproduct is water vapor. No combustion, no NOx, no carbon emissions at the point of use. But here's where helicopters are fundamentally different from fixed-wing aircraft, and why you can't just drop a fuel cell in and call it done. Helicopters operate under highly variable power loads. Takeoff, hovering, and maneuvering all require sudden spikes in power demand that are completely different from cruising flight. A fuel cell alone can't respond fast enough to those transient loads. The electrochemical reaction has a response curve. It ramps up, but not instantly. So the architecture adds a battery buffer. The fuel cell handles steady-state power, the baseline load during cruise and stable hover. The battery handles the peaks, those short, high-demand moments that define rotorcraft operation. This isn't a workaround. It's the correct engineering solution. The two systems do different jobs, and together they cover the full operating profile of the aircraft. The hydrogen itself is stored on board in tanks. We'll get into the specifics of that in a minute. And it feeds the fuel cell continuously during flight. Think of it like this. The hydrogen is the fuel reserve, the fuel cell is the generator, and the battery is the surge protector. Each element plays a defined role, and the system only works well when all three are properly coordinated. Here's where most coverage stops and where we need to go deeper. Because saying they're refining the system doesn't tell you much unless you understand what that actually means in practice. The first focus area is power control, specifically coordinating energy flow between the fuel cell and the battery in real time during flight. This is a software and electronics challenge as much as a mechanical one. The system needs to anticipate load changes, shift power sourcing between the two components seamlessly, and do all of that without introducing latency that the pilot would notice, or that could affect aircraft stability. Getting this right under the full range of flight conditions, including emergency scenarios, is one of the hardest parts of the entire program. The second area is weight and integration. Hydrogen storage tanks, cooling systems, power electronics, the fuel cell stack itself. These all take up space and add mass. And helicopters have strict weight limits and very specific balance requirements. If the center of gravity shifts, the aircraft handles differently. So the engineering team isn't just packaging components, they're doing it within a very constrained design envelope, and every kilogram matters. The third area is thermal management. Fuel cells generate heat as a byproduct of the electrochemical reaction. On the ground, that heat can be managed relatively easily. In flight, with variable airflow, altitude changes, and fluctuating power demands, keeping the fuel cell within its optimal temperature range is a continuous challenge. If the stack runs too hot, performance degrades and component life shortens. Too cold, and the reaction efficiency drops. Managing that thermal window in a dynamic flight environment is genuinely difficult engineering. And then there's certification alignment, which is less about building the technology and more about building it in a way that regulators can verify. Every design choice needs to be traceable, documentable, and testable against a defined safety standard. This shapes engineering decisions from the very beginning, not just at the end. Companies that treat certification as an afterthought tend to rebuild large portions of their systems later. Robinson, with decades of certified aircraft production behind them, understands this deeply. Let's talk about hydrogen storage because it's one of the most consequential decisions in the program, and it's still being worked through. There are two primary pathways currently under consideration. The first is compressed hydrogen gas, hydrogen stored at high pressure in reinforced tanks. This approach is more mature, more widely used in ground-based applications, and simpler to implement from a handling and infrastructure standpoint. The trade-off is energy density. You can only store so much hydrogen in a given volume at pressure, which limits how far or how long the aircraft can fly. The second pathway is liquid hydrogen. Hydrogen cooled to extremely low temperatures around -253 degrees Celsius and stored in cryogenic tanks. Liquid hydrogen contains significantly more energy per unit volume than compressed gas, which translates directly into longer range and greater payload flexibility. But the handling requirements are substantially more complex. You need specialized ground equipment, trained personnel, and infrastructure that simply doesn't exist at most operational sites today. For the early program, compressed hydrogen is the more likely near-term choice, primarily because it allows flight testing to proceed without solving the entire infrastructure problem simultaneously. Liquid hydrogen is likely a future direction as the technology matures and the supporting ecosystem develops. The storage decision doesn't just affect what the aircraft can do. It affects where it can operate, how it gets refueled, and what kind of logistical chain needs to exist around it. That ecosystem question is something we'll come back to. One of the most important things to understand about any emerging propulsion technology is that it doesn't go everywhere at once. It goes where the conditions are right first, and it expands from there. Hydrogen helicopters are no different. The environments where this technology is most viable earliest share a few characteristics. They tend to have controlled, predictable operations, meaning the aircraft flies relatively fixed routes or missions, rather than unpredictable ad hoc deployments. They have centralized infrastructure, meaning hydrogen can be stored and managed at a specific base or facility, rather than requiring a distributed network of refueling points. And they have high mission value per flight, meaning the cost premium of hydrogen over conventional fuel can be justified by operational, regulatory, or reputational factors. Emergency medical services fit this profile well. Offshore transport, servicing oil platforms or wind installations, fits even better. Industrial inspection and utility corridor work also qualify. These are not small markets. And critically, they're markets where the operators already deal with complex logistics, specialized fueling, and strict regulatory requirements. Adding hydrogen to that picture isn't a complete operational overhaul. It's an incremental shift in fuel type within an already disciplined operating environment. Here's the honest read on where this program stands. And this is the part that doesn't make it into most coverage. The aircraft system is progressing faster than the surrounding ecosystem. That's not a criticism. It's a structural reality of how deep technology transitions work. The fuel cell integration, the electric propulsion control architecture, and the hybrid energy management system are all advancing on a defined engineering roadmap. Robinson has the expertise, the regulatory relationships, and the manufacturing discipline to see that through. What's still developing, and developing on a separate, slower timeline, is the hydrogen supply chain. Refueling infrastructure at operational sites, consistent fuel availability at the locations where these aircraft would actually be based, cost stability and green hydrogen pricing, the logistics of handling compressed or cryogenic hydrogen in a field environment. This gap doesn't stop development. Robinson doesn't need hydrogen airports to exist before they can fly the aircraft, but it does define where and how early adoption happens. The first operators of a certified hydrogen R66 won't be randomly distributed across the industry. They'll be the ones with the infrastructure capacity, the operational discipline, and the strategic reason to absorb the early adopter friction. And that's not a small group, it's actually a well-defined one. And this is exactly the layer most coverage misses. Not the technology, but how these systems actually get built, financed, and deployed in the real world. If you're working on hydrogen projects or trying to understand what actually makes them viable beyond the headlines, I've put together deeper breakdowns inside H2 Hub by Renee Energy. So, where does this leave us? Robinson's Hydrogen R66 program is a real engineering program, moving through the hardest phases of development. Not the most exciting ones, but the most important ones. The physics work. The architecture is sound. The certification path is difficult but understood. The main challenges aren't fundamental. They're integration, weight, thermal management, and the slow build of the surrounding infrastructure ecosystem. Those are solvable problems. They're being worked on right now. What this program ultimately demonstrates is that hydrogen propulsion in rotorcraft isn't a future concept waiting for a breakthrough. It's a near-term engineering outcome waiting for a convergence between the aircraft system, the regulatory framework, and the ground infrastructure that makes it operationally practical. That convergence is coming, and Robinson is positioning to be there when it does. If you want to go deeper on any of the technical systems we covered today, fuel cell architecture, hydrogen storage trade-offs, or the certification process, drop it in the comments and we'll build that out. And if this kind of technical signal over noise energy coverage is what you're here for, subscribe and I'll keep bringing it.